In June of 1972, a lab technician in the south of France runs a routine test on a shipment of uranium and gets a result that should be physically impossible. Every gram of natural uranium anywhere in the universe, mined from the ground, pulled off the moon, carved out of a meteorite, carries exactly the same signature. 0.7202% of it is the fissile isotope UA235, always no exceptions. This sample comes in at 0.7171. That's it. That's the whole crime scene, a difference so small you'd need a laboratory to even see it. But nuclear material doesn't get to be a little bit missing. When French investigators do the math across the entire shipment, the gap adds up to about 200 kilograms of weapons-grade uranium, unaccounted for, enough to build half a dozen bombs on the scale of Hiroshima. And the trail leads back to a patch of dirt in Africa that had, it turns out, already built its own nuclear reactor 2 billion years before humans figured out what an atom was. The analyst's name was Jean-François Bouzigues, and his job that day was about as unglamorous as nuclear physics gets, running mass spectrometry on uranium hexafluoride gas from a mill in Gabon, checking boxes. Instead, he tripped an alarm across the entire French Atomic Energy Commission. In an industry where every fraction of a gram of fissile material is tracked, licensed, and locked down, 200 kilograms is not a rounding error. It's a 5-alarm fire. The first assumption was the obvious one. Someone stole it, the batch got contaminated, or a middleman swapped in depleted uranium somewhere along the supply chain. So investigators start walking the chain backward. Mine to mill to processing plant, hunting for the leak. But the deeper they dug, the less it looked like theft. Direct samples pulled from the mine itself at a place called Oklo came back even stranger. U-235 levels as low as 0.44%, far below anything a thief would bother leaving behind. Physicist Francis Perrin, who used to run the entire French Atomic Energy Commission, looked at the raw ore and found something that had no business being in a hole in the ground in Gabon trace: amounts of neodymium and ruthenium, sitting in ratios that only show up in one place on Earth: spent fuel rods pulled from an operating nuclear reactor. The uranium hadn't been stolen. It had been burned. Somewhere in the back of Perrin's memory was a paper from 1956, written by a physicist named Paul Kazuo Kuroda, who had run the numbers on a wild hypothetical: could a natural uranium deposit, under exactly the right conditions, spontaneously start a chain reaction on its own? 16 years earlier, everyone had treated it as a curiosity. Now Perrin was standing in front of the proof. So how does a patch of riverbed with no engineers and no blueprints build a nuclear reactor by accident? You have to go back further than the reactor itself. Back about 2 billion years to a version of Earth that would barely be recognizable. There were no plants, no animals, nothing with a spine or a shell. Just water, rock, and the first generation of cyanobacteria learning how to turn sunlight into oxygen. That single development, known as the Great Oxidation Event, is the reason any of this happened at all. Because uranium doesn't dissolve in water unless that water carries oxygen. Once it did, uranium started washing downstream into a river delta in what's now Gabon, where it ran into pockets of petroleum-soaked sediment. The organic material reacted with the oxygen, and the dissolved uranium dropped straight out of the water, layer after layer, concentrating into thick veins of ore. And here's the detail that turns this from lucky to almost unbelievable, because the universe was younger and less U-235 had decayed away. That ancient ore sat at roughly 3% enrichment. That's not a rough estimate. That's the exact enrichment level engineers manufacture in centrifuges to fuel a commercial reactor today. Nature hit the number first. An unshielded deposit of enriched uranium sitting in wet sand with nobody around to regulate it should have been a one-way trip to disaster. Modern reactors survive because engineers packed them with control rods made of boron or cadmium, materials built specifically to soak up stray neutrons before things run away. Oklo had none of that. What it had was groundwater. Picture skipping a stone across a pond, throw it too fast, and it just skips off the surface without sinking. That's roughly what a fast neutron does when it hits a uranium atom too quickly to be absorbed. But groundwater flooding through the porous rock slowed those neutrons down, the way deep water catches a stone instead of letting it skip. And slow neutrons are exactly what a chain reaction needs to sustain itself. As fission kicked in, the rock heated past 300 degrees Celsius, pressure climbed to 150 atmospheres, and the groundwater boiled away into steam. No water left meant no moderator, which meant the chain reaction shut itself off automatically like a geyser running dry. Then, over the next 2.5 hours, water crept back in and the whole thing lit up again. In 2004, a researcher at Washington University named Alex Meshik proved this timing down to the minute by studying xenon gas that had been trapped in the rock since the reactor last ran. 30 minutes on, 2.5 hours off, for over 150,000 years. It ran unsupervised in the dark for 15 to 30 times longer than the whole of recorded human history, and the harder question might be what happened after it finally stopped. Eventually, the U-235 thinned out too much to sustain the chain reaction, and the reactor went quiet for good. Left behind was a chamber full of exactly the kind of waste that keeps modern nuclear engineers up at night. Cesium, barium, xenon, krypton, some of the most dangerous radioactive material there is. By every modern assumption, that waste should have leached into the groundwater over 2 billion years and gone wherever water goes. It didn't move. Minerals in the surrounding rock, aluminum phosphate, ruthenium sulfide, locked those elements down at a molecular level and never let go. Not through ice ages, not through the entire rise of complex life on Earth. Engineers designing deep storage sites today, from Yucca Mountain in the United States to Olkiluoto in Finland, are essentially studying Oklo's homework. Nature already ran the experiment. Humanity is still afraid to trust. There's something almost unsettling about that. The idea that our biggest fear about nuclear power, that the waste can never really be contained, was already answered, quietly underground, before there was anyone around to be afraid of it. Geologists think the conditions that built Oklo weren't unique to one river delta in Gabon. The same basin has a geological twin sitting on the other side of the Atlantic in Brazil, split apart by continental drift 100 million years after Oklo went cold. So, if it happened once by accident with nobody watching, what else is still running down there in the dark that we simply haven't found yet?